I want to thank the organizers, if they are assuming some of them are here, for inviting me to give this talk. It's a terrific meeting, as always. But this time, it seems like the topics are a lot more diverse than I remember the last one a few years ago before the pandemic. I'm going to talk about a very specific problem and a very specific experiment and that we heard about yesterday, and I'll describe that in a little bit more detail than Case actually did. And this pertains to loop extrusion by condensins. Possibly a similar theory would hold good for cohesion as well, although we've not really tried to think about that, because I don't know of experiments of the kind that Case, in fact, reported for condensin about 5 years ago. We heard a lot about SMC complexes yesterday and today as well, in connection with replication fork stability. And apparently, from what I learned from both Case and Leonard Murney, there are more and more intriguing things that condensins actually do than we have learned so far, and perhaps there are a lot of surprises. The guys with whom I did this work are these three. This Ryota graduated about a year plus ago, maybe a year and a half ago. He's in Dresden. Guangxi is in Illinois, and he's about to graduate. And these are the two relevant papers that I'll discuss with you today. So, like I said, the Case, in fact, listed about 20, 30, 40 different results yesterday about what condensins actually do. And in fact, even Murney listed a bunch of things. The idea that some motors consuming ATP molecule, I don't know when the ATP part actually became known, must extrude some loop as a mechanism of condensing interface chromosomes by cohesin and mitotic chromosomes by condensin. Apparently has been known for quite a while. But in the modern incarnation, I think Marco and followed by Erez and our own chair put forward a mechanism of translating that picture of loop extrusion into something algorithmic that you can probably compute things with. So these are pictures we saw yesterday. This is from Murney's paper in 2016, and this Erez showed this. In fact, he even showed a movie. There's some amount of similarity between the two, but they're all pictures and condensin, or say cohesin, but I'm going to just focus on condensin, would land orbitally at some spot on the DNA, and then it would probably undergo ATPase cycle, and as it undergoes ATPase cycle, consuming one ATP per molecule per extrusion length, it extrudes loops, and this process, if it allowed to continue consuming multiple ATPs, one can imagine the loop growing almost indefinitely. Of course, this doesn't happen in real life. There are multiple motors, and there must be some communication between the motors that allows it to stop. And in the mechanism that one can envision is that when it encounters some kind of a CTCF or something like that, in the cohesin case, some obstacles, it would stop. So this is the experiment that I'm going to try to explain to you, and this is Case Dicker's experiment from about 5 years ago. I think he showed bits of this yesterday very, very quickly. This is a DNA molecule that's tethered at two ends. In some sense, one might think this is not really what happens in real life because it's not tethered at two ends. And then there's a flow, which mimics essentially the force, and presumably there's ATP involved. Without that, the motor wouldn't function. And the loop is extruded, and there's a very nice movie. I think he showed that yesterday as well. So what's measurable, in some sense, is the velocity with which the loop is extruded as a function of relative DNA extension. And the extension, if the DNA is modeled as a worm-like chain, is in fact related to the force through the Markov-Sigia formulas, and therefore this velocity as a function of force is a force velocity curve, in fact, can be inferred from an experiment of the kind that that case actually did. So what you see here is the velocity decreases with the external force, which is resistive in this case, and therefore around some stall force, which is of the order of about a piconewton, the velocity goes to 0. In the sense, it's a very wimpy motor, unlike the motors that we normally study, which carry cargo like kinesin, myosin, and dynein. So the objective that we set ourselves was to calculate these quantities that are measured in experiments, and we've been working on motors for quite a long time. And so following our work on myosin 5, which we first reported somewhat 10 years ago, and followed this up about another 3 years ago, we could compute the force velocity curves of myosin using some kind of a polymer theory. Some of it I'll tell you this in a little bit later, and we could also calculate step size distributions. Myosin is a dimeric motor that works on F-actin from the minus end to the plus end. Takes about 36 nanometers per ATP consumed, which means this motor has to traverse 72 nanometers roughly to cover this 36 nanometers. But there's a distribution in the step size, and the distribution is quite small in some sense. It's a little bit larger than what it is in kinesin, but this distribution, as you'll see, is much, much smaller than what condensin does. So we want to be able to calculate things like this for condensin, and that's what I want to tell you about. I knew about this mechanism called the scrunching mechanism that Case mentioned yesterday, but I knew it in the context of the bacterial transcription that was reported in 2006 in 2 back-to-back papers in Science. And if you read the first sentence, in both these papers, they sound exactly the same, using FRET, etc., to monitor distances within single molecules of abortively initiating transcription. We show that initial transcription proceeds through a scrunching mechanism in which RNA P is stationary on the promoter DNA. It pulls downstream DNA into itself and passes active center. And if you read this sentence here, it more or less says exactly the same thing. So the idea is the polymerase, in this case, does not move, at least the leading edge of it, but it reels in the DNA, and then there's a bubble opening, and then the template strand is actually synthesized. A few years later, in 2010, my former student and Seth Dars, who is in Rockefeller, and I published this paper trying to really put some more structural details into this experimental findings, and let me show what scrunching means. This is a cartoon picture, but all these, the promoter is from minus 40 to plus 25, and the start side is plus 1, and the upstream DNA is negative, and the downstream DNA past the start side is positive. And what they measure is a FRET efficiency between various sites on the polymerase and the DNA and the DNA and the DNA. So there's a number of experiments have been done on this, and the point is that if you measure distances between the polymerase and the upstream DNA, which are negative, they actually don't change at all. For example, and this is a calculation that we reported, that the distance FRET efficiency is roughly a reporter of the distance. And if you look at the distance between the polymerase and the minus 39, which is downstream, upstream, it doesn't change. But if you look at the plus 20, it changes, and the DNA conformation actually changes, which means that the leading edge of the polymerase is essentially stationary, and you have the DNA actually reeled in. So this is the scrunching mechanism we want to adopt for condensin. It's not as precise in condensin because there are hints in the 2018 paper with Ganji and his company in Case Decker that it must be scrunching, and that's what he mentioned yesterday. So this is a cartoon of condensin. Its dimensions are roughly about 50 nanometers. The heads are somewhere here, and we talked, and we learned a lot about nib-BL and deletion of nib-BLs and so on and so forth. And they're all associated with interactions in the head domain. And the hinge is roughly about 50 nanometers away, so you can think of this as a molecule that can reel in 50 nanometers plus minus something of DNA, which is quite a lot, but in fact, the distribution of the loop extrusion is much greater than that. It also, like our three motors, consumes 1 ATP per turnover, and that's established. But the ATP cycle is not characterized for this machine. By that I mean, we don't know the structures of these condensin molecules in various nucleotide states, which is what has been determined to some extent in kinesin and myosin, enabling one to actually produce quite a bit of structural work. I mean, Jose has done in his team over the years quite a bit of work on in both kinesin and possibly myosin as well. I don't remember. So that makes it a little bit difficult, and so therefore I would argue that much less is known about condensin than compared to these motors, although even in these motors there are interesting problems that have not yet been solved. So we're going to translate that cartoon into a model where we can calculate things. So we're going to assume this A is roughly your head, if you wish, and the red, B, which is red, is roughly the hinge, and the DNA molecule is this thread. And say L0 is some initial loop, and it can be 0. And R1 is the distance, which is roughly about 50 nanometers in the cartoon that I showed you before. And ATP binds to the heads here. And the assumption that we make is that the angles involved in this, in the inter-head expands. That triggers an allosteric transition, which then pulls this hinge part down, and there's some amount of flexibility in the SMC loops, which we treat as a semi-flexible chain. So when that happens, the distance decreases, R2, and the loop is actually extruded, and the increase in the loop length is roughly L1 minus L2. That's a physical picture, all right? So in order to calculate, like others in the before, I'm not going to show many equations. What you want to know is how much loop is actually extruded when the distance between the DNA is of the order of R or delta R in the previous slide. We had calculated some time ago for worm-like chains what the end-to-end distribution is for the contour length, and that's this analytic formula. It works pretty well. The exact relationship is also known, but this suffices. But what we want is something slightly different. We want to know, given R, how much loop can you extrude? And so this one can calculate. And it turns out that has a heavy tail distribution, but roughly speaking, we basically used essentially for analytic theory that the delta L amount of loop extruded is roughly of the order where this actually peaks. And that turns out to be of the order of the dimension of the average distance between the head and the hinge, which is about 50 nanometers, although the distribution of the extruded loop is considerably larger, as I shall show. So once you have the physical model, we know it consumes ATP, so the thermodynamics for condensin, this would be the same thing as the thermodynamics for kinesin, for example, is it does some work in order to extrude some loop. It's locally stiff in any event, unless the L0 becomes very large, then it's flexible, so you got to do some work, even in the absence of external force, to extrude loop of some length. And then if you have an external force, you got to compute how much work is actually done to extrude that loop. And the energy input is the chemical potential due to ATP hydrolysis, around 20 kBt or so, and the energy conservation dictates that should be equal to the work plus heat dissipation. And then once you, this is just thermodynamics, and then from there, you could actually work out what the rate or the velocity should be, because there's a fluctuation theorem that actually relates these quantities, and the final result, in fact, is quite simple, and one could have derived this from dimensional analysis, that the velocity would be something that's related to the k0, which is the ATP hydrolysis rate. Delta R is how much the hinge, in fact, approaches the head, and these are factors that arise from the external force, if there is an external force. There are two parameters in this theory. We don't know what the ATP hydrolysis rate is, and we also, in principle, don't know what delta R is, and that's the amount this actually moves, although Case, in fact, has measured this, and I'll show the comparison with his data. This is the velocity of the motor in kilobase pairs per second as a function of extension, and if you want to convert this to force, we simply use the Markov-Sigia formula for some given persistence length, and the red dots are from Case's work, and this blue is our result. I think these experiments could be made more precise to get better velocity. This is typically the case when you look at motors, like myosin, for example. So when you fit this to the experimental data, and because of the uncertainty, the ATP hydrolysis rate that we pull out is about 10 to 20 per second. The delta R, the amount that this guy actually moves, the mean value of that is about 26 nanometers. Experimentalists believe that the condensin motor ATP hydrolysis 2 per second. I actually don't believe it's so low, but we don't know that very well. The other, this was reported in 2018, and then a couple of years later, Case Decker also calculated or measured, in fact, the distribution of the extruded loop as a function of delta L for various values of force, and this is for force equals 0.4 piconewtons. Remember, this motor stall force is about a piconewton or so. And this red is our calculation, and the histograms are taken from his experiment. In the insert, we show an older experiment that Tatsuya Hirano had also actually measured these distributions, and they're not that dissimilar. I think this is at the lower force, or maybe even zero force, I really don't know. The bottom line is this very simple model based on the assumption, once landed, it extrudes loops without moving very much on the motor, on the track, which is a pretty soft track compared to, for example, a factin or microtubule, explains the experimental data quite quantitatively, or good enough in any event. What about this delta R? Because we wanted to see if we can devise a simple-minded picture based upon the scrunching mechanism. So we created this little model. You have a head, you have a hinge, worm-like chain, some flexibility here, and the two states are the open states and closed states. Incidentally, Case mentioned this as well in a paper prior to the 2018 paper. They reported AFM images where they showed that the motor could exist in two or probably even more states. One of them is closed. I think the other is open. I'm just going to call this a closed state and open state. They have some other terminologies, B and O and so on and so forth. The idea is when ATP binds, it expands its angle. Once it expands its angle, that's a little bit of a strain. That strain has to propagate. It propagates through the worm-like chains, and then it brings this hinge and the head close together, and that's the allosteric mechanism they envision. And once you write down the energy function based upon this model, you could actually do some kind of a Brownian dynamic simulations. And that's what one of my guys did. And then you can calculate for multiple realizations, not just one value of this distance, but the distribution. And this is the distribution that we calculated, and this is what's reported in this particular paper in Nature Structural Biology, and that's from Case Decker's group as well. And the peak distance is about 22 nanometers. That it coincides with this. It's a little bit too much because we could adjust the persistence length quite precisely. I must say that the persistence length we chose is about 4 times larger than in order to get this agreement than what case reports, and I mean, I think that jury is out in my head as to what the exact persistence length is under the conditions of operation. Okay, so in fact, I could say that with the simulations and the theory, we have only one parameter, but in any event, the theory accounts for the force velocity in the distribution curves. But the theory also makes additional predictions for which experiments have not been reported. For example, the velocity will depend upon the ATP concentration, and I don't remember what the ATP concentration is in the 2018 paper, maybe Case does, but now we calculated these are predictions, the velocity of the motor as a function of ATP concentration for various values of force, and force, of course, is the same as extension via the Markov-Sidger relation. And you can see that as force increases, or for a given ATP, the velocity, in fact, can decrease quite a bit. And hopefully, someone will do the measurement. And this is a distribution, again, for different values of force. That's 0 up until about stall force. And the width of this distribution is quite broad, even though it's peaked around 40 or 45 nanometers, but the width is about 30 nanometers. In fact, the theory and as well as experiment predict that with one ATP consumption, it could extrude loop, which is of the order of even about 100 or 80 nanometers. I think that's surprisingly large compared to, for example, myosin, where the distribution is much narrower. Kinesin is believed to be even more narrower, where it takes a discrete steps of about 8.2 nanometers per ATP consumed. Right? So what about comparing the motors? These are the force velocity relationship curves experiments. And this is from Yanagida, this is from Block, this is from Carter and Cross. And you know, they're not all superimposed, but this is a biology kind of experiment. But if you look at kinesin, the maximum velocity at 0 external force is about 800 nanometers per second. The stall force is about 8 piconewtons. ATP hydrolysis rate about 100 to 500 per second, depending upon the concentration. In myosin, the peak velocity is about 400 nanometers per second. The stall force is about 2 piconewtons. ATP hydrolysis rate is about 750 per second. The velocity of condensin is quite comparable to myosin 5. This is myosin 5. But the stall force is very little. And even if you say that the ATP hydrolysis is 20 per second, it's still much smaller than the conventional motors like kinesin and myosin 5. The origin of such a low hydrolysis rate is not understood. I mean, I don't know in any event, and we'll need structures in both the APO state, ATP bound state, ATP hydrolyzed states in order to sort this out. But it's pretty unusual in this sense. Incidentally, if you make a naive estimate based upon the stall force about the efficiency of the motor, condensin is not as efficient as myosin. It's only about 50% efficient or something like that. I'm done? Okay. Plus, minus, right? All right, good. That's it. I'm good. I'll stop in 2 minutes, right? Okay. So I'm done, so I'm not going to be able to tell you anything else. I had all these other things to tell you, but I'm not going to tell you that. I'm going to conclude here because Leonard says I should get out, and that's fair. And these are the conclusions. I think from a theoretical perspective, right, and the experimentalists keep moving on from one thing to another. From a theoretical perspective, there's a long ways to go before we actually sort out a single condensin motor, determine its ATP cycle, couple it with loop extrusion, and get to the level of understanding that we sort of have for example, kinesin or some other motor. And that adventure for kinesin has taken 30-some years and it's still not totally done, because this year alone there was a paper, 2 back-to-back papers in Science in March that in fact dug out some other nuances about kinesin, how it in fact waits for ATP, both coming from Germany, Stefan Hell and somebody else. So given that the dust has not settled on kinesin, I expect that it'll take another 30 years before a single condensin is understood, but the experimentalists, of course, have to think about real biology. Thanks very much.
Hi, Dave. Great talk. Can you speculate on, the part of the discussion yesterday by Case revealed this 0.6 twist per cycle. I think that was right, something like that. I guess what I'm wondering is it possible that just through the mechanics of the SMC and where it would land on the DNA and sort of how much it fluctuates given the persistence lengths that you have, can that sort of explain through just kind of a docking and twisting sort of mechanism why it would have, some sort of stable, average twist that it could impose? I mean, in your model, you have, the bending and everything, but if you incorporated an additional twist that would allow the docking, can you just speculate on that?
Well, I mean, as you know, one could actually do that calculation because it's not super hard, and it'll introduce one more parameter in front, and then, of course, you want to know how to compute that, and for that, you need a good data, right? And I haven't quite looked at Case's experiments in that to see how good the data is to worth our while to do such a calculation. I mean, but it's doable. Yeah. I mean, it's very straightforward, in fact, actually.
Hey, that was a really wonderful talk. I had a question about oligomycin experiments. So
what?
Oh, I had a question about oligomycin experiments. So oligomycin inhibits ATP synthesis, and we and others have done experiments looking at in vivo loop extrusion in the presence and absence of oligomycin. And I wonder if you've looked at those experiments. They could potentially, I mean, you were talking about, for instance, the effects of ATP concentration on velocity, and I wonder those experiments might be able to, I don't know if you've looked at them, but.
No, I'm not actually. I mean, I've been looking for data to see what the velocity as a function of ATP concentration is, because that's what we calculated, and it'll be great to have data on that. We know that it has a significant effect at physiological concentration of ATP, 150 millimolar, something like that. The velocity decreases by a factor of 4, which is quite a lot, actually. So I'd like to know about.
We didn't, at least in our version of this, didn't explicitly calculate the resulting ATP concentration, but it's certainly very doable. In vivo in a degron setting.
It'll be great.
That was a very nice talk, Dave. But I have one question that we know from kinesin. Not necessarily the force-dependent step is the one that determines the velocity, right? You can have another step. Kinesin, for example, you expect maybe some other step to keep the velocity more uniform. Is that not the case for condensing? Can you actually do all this? Be sure that the force-dependent step, the one that determines the velocity of the motor?
But I think there's a basic difference in the condensin, in the kinesin versus condensin. In the kinesin case, the track stiffness is about 1 millimeter or something. Here it's 50 nanometers. And so the things that we envision should happen, not envision, we know happens in kinesin, simply doesn't happen here because of this extremely soft track.
So you think that the velocity is determined for this force-dependent step of the cycle?
Yeah. And that piece of it is clearer here than in motors, conventional motors. But there are lots of other things which are not as clear.
Okay. If there are no more questions, let's thank Dave again.